All right, Assalamu alaikum. So I'm just gonna switch off my video and I'm going to turn on the screen sharing.
Okay.
So here is my. All right. So what I'm going to do today is I'm going to describe the Hamiltonian, which is relevant to free electrons, but these electrons are interacting with one another. So although we are going to talk about free electrons, but these are interacting electrons. We have sea of electrons which are interacting with one another through the Coulomb repulsion. In this course, at different occasions, we've already discussed and we've seen free electrons in various lectures. Today, we're going to use the second quantization formalism to describe these electrons. In particular, we're going to derive a Hamiltonian, which is based upon creation and annihilation operators. So in order to begin our discussion, first of all, we would like to kind of revise or introduce ourselves to a new way of representing multiple electrons, which are all identical particles. Generally, what we do is we would like the wave function of the electrons being fermions to be antisymmetric. So if we focus our attention on two electrons, the wave function can be written in this fashion. The quantum state psi alpha 1, I'll describe alpha 1 or alpha 2 in a minute. Psi alpha 2 R2 minus psi alpha 2 R1 psi alpha 1 R2. Just a second, let me reduce this a little bit. So I also need to normalize. This is my two particle wave function. Alpha 1 and alpha 2 are the quantum states for the two particles. And the first particle is at location R1. Second particle is at location R2 in the first term in the superposition and vice versa in the second term. And we form this linear combination of terms to make the overall wave function psi R1, R2 antisymmetric. So this is an example of a two-particle wave function. Overall, this is antisymmetric with respect to exchange. All right, so far so good. So if you would like to extend this to a higher number of particles, what we could simply do is take the same idea and move on to n particles. At this stage, it will be very cumbersome to write down the entire superposition. So we write this wave function as a determinant. And that determinant is given by psi alpha 1 R1 psi alpha 2 R1 psi alpha 3 R1 all the way up to psi alpha n R1. In the second row, we have psi alpha 1 R2 psi alpha 2 R2 psi alpha 3 R3 psi alpha n R sorry, all of these should be R2, and so on. Finally,
Sir,
we have psi
yes.
alpha 1 Rn, psi alpha.
सर एक छोटी सी बात पूछनी थी।
जी जी जी।
सर जो पहले वाला हमने केस किया था उसके अंदर हमने ये अजम्पशन ली थी कि फ्री इलेक्ट्रॉन्स जो हैं वो आपस में इंटरेक्ट नहीं कर रहे, या वो भी मतलब फॉर मतलब इंटरेक्टिंग था?
इंटरेक्शन हो या ना हो, उससे फर्क नहीं पड़ता। सिमेट्राइजेशन पॉस्टुलेट तो सेटिस्फाई होना चाहिए, यानी ओवरऑल वेव फंक्शन फ्री और इंटरेक्टिंग इलेक्ट्रॉन्स का ये एंटी सिमेट्रिक अंडर एक्सचेंज रहना चाहिए।
ठीक है, ठीक, सही।
इसी तरह सो दिस इज द फाइनल रो psi alpha 3 Rn, psi alpha n Rn. All right, so this is a determinant which is generally called the Slater determinant, and this describes n particle states. So if any two rows are equal in this determinant, the determinant just vanishes, which is actually another way of saying that the Pauli exclusion principle is satisfied. Now, this is a very cumbersome notation. So we would like to move to another notation, which we like to call the occupation number representation. Now, in the occupation number representation, things get slightly simplified. So we have a number of particles, and there is a variety of quantum states in which those particles can exist. And we just count the number of particles in each quantum state. So if we have a quantum state alpha 1, we count the number of particles in the state alpha 1. Then we count the number of particles in the state alpha 2, alpha 3, and so on, until we have counted the particles, number of particles in all the quantum states. From alpha 1 to alpha n, we put all of this in a ket. This becomes our n particle quantum state. So, for example, if we have two particles, and those particles say are bosons, then we can have one particle in the state alpha 1, and we can have another particle in the state alpha 2. This is one example of a quantum state. We can have two particles in the state alpha 1, zero particles in the state alpha 2, and so on. For fermions, of course, n could either be 0 or 1 for any alpha. So therefore, it becomes really simple for fermions. That is, the n particle wave function, the quantum state, is just a string of zeros and ones. And if we talk about electrons that are free, or just see a positive homogeneous mixture of charge due to the ions, which is generally called the jellium model, then each of these quantum states, each of these alpha states, is actually a combination of a wave vector k as well as spin. So alpha is just a shorthand for the wave vector or the momentum and the spin if we are in the Fourier space. So this is the occupation number representation. We can also define a quantum state, which is the ground state, which is called the vacuum state. The vacuum state is really that there are zero particles, in any state. So there are zero alpha 1 particles, zero alpha 2 particles. There are no particles whatsoever. This is called the vacuum state. And in shorthand, we just write a big zero for this. Now, if you want to create an n particle state, we can easily move upwards from the vacuum state. For example, if I have the vacuum state and I have a creation operator which creates a particle in the state alpha 1, then I will get one particle in the alpha 1 state. I can also do a sequential creation of states. So I create a particle in the alpha 1 state, then I create a particle in the alpha 2 state, and so on. So starting from the vacuum state becomes like a fiducial state. It is a ground state, and all the states can be built upward from the fiducial state. And all the number states can be formed by the action of creation and annihilation operators on the vacuum state. But if you start with the vacuum state and you have an annihilation operator, the output is just zero. So you have a sequence of creation operators to create any state that you desire. Now, electrons are fermions. So when we talk about fermions, there are special fermionic commutation relationships that we must be cognizant of, right? So they are unlike fermions, they're unlike bosons, sorry. They are very different from the magnons that we've seen, and they have special behavior. For example, if I have the vacuum state and I have this operator C alpha 1 dagger, C alpha 2 dagger. So what this means physically is that I'm creating a particle in the alpha 2 state followed by the creation of a particle in the alpha 1 state. Suppose this gives me some state psi. Now, if I reverse the order of creation, so I have C alpha 1 dagger followed by C alpha 2 dagger, then this state will be totally different from the initial state. So the order in which the creation operators are applied is important. So order is important. This is not true for bosons. So, and everything really, and how can you show that the order is important? So if I take either this state or this state and have uh, a C operator, say alpha 1 annihilation operator, act on, say, this state here, then I will get some new state, phi. But if my C alpha 1 operator acts on this state, C alpha 2 dagger, C alpha 1 dagger, I get another state. And you can show that this is going to be the negative of the original state. So the order is important. And this is true for fermions. And this is something that you can prove on your own. And everything really stems from the commutation relationships. That is, I have the anti-commutator of two fermionic operators, C alpha, C beta dagger. The anti-commutator is given by the Kronecker delta alpha beta. So for bosons, we know that we have a situation of this kind. The commutator is the Kronecker delta. So all the properties stem from the commutation relationship. ठीक है हमजा? So
Yes, sir.
so
Thank you.
so now we move on. So everything is quite evident here. So just to give you as an example, if I have an n particle state psi, which is formed by the creation operators acting on the vacuum state. So I'm creating a particle, one particle in each of the n quantum states. Suppose I call this my quantum state psi. Now what happens if I take this psi and onto this psi, I implement the annihilation operator. So what the annihilation operator does is that it kind of annihilates a particle which is in the state alpha I. So if this is my original state, then at the ith position, the number of particles will be decremented by 1. So previously I had n alpha I particles in psi. Now this annihilation operator decrements this by 1 and keeps everything else the same. Correct? And I need some normalization factor with this as well.
Yes, sir.
And then I also have, because these are fermions, I also need to add a phase, nu I. So this nu I is the sum of n alpha k, where k goes from 1 to I minus 1. Okay, likewise, if I have state psi and the creation operator acts on this, n alpha I just increments by 1. And I need to kind of have some normalization factor and some phase as well, where nu I has the same definition in both of these cases. So all of this is really clear. So in the first example, if you see that if your original n alpha I were 0, then the state just disappears. So it annihilates the vacuums, it annihilates the particle. If there were no particle here, 0 particles here, the output for the annihilation operator acting on the state will just disappear. So all of this is actually so far really clear. And I can also see what the impact of Ci dagger Ci on psi is going to look like. And this you can do as a homework. This will simply be the number of particles in the state alpha I. All right, so this is something for you to prove on your own. So this is a number operator on the alpha I state. It gives the number of particles in that state. And I can also define a number operator n, which is the sum of all the Ci dagger Ci's. Okay, so this is the basic machinery for the second order quantization. Now I would like to, now that we know how states are formed, let's move our attention towards the second quantization form of operators. Now, why are we doing this? We are doing this because we would like to write down the Hamiltonian for electrons, interacting electrons that are otherwise in a constant homogeneous potential formed by the positive ions in the second quantization form. So in order to motivate the idea of the second quantization of operators, let me give you a few examples. So the first example I like to present is of a single particle operator. Single particle operator. All right. So suppose I have an operator A in the first quantization picture. When I upgrade this to the second quantization picture, this A becomes A sandwiched between two states, alpha and beta, and the operators C alpha dagger, C beta. So this is the second quantization form of a single particle operator. A single particle operator means that it only depends upon the coordinates of one particle. So this will become clear if I give you some examples of it. So suppose I have the momentum operator and I want to find the second quantization form of this operator. So I can choose two states, alpha, beta, to be the momentum eigenstate. So I take the momentum operator and sandwich between two momentum states, P1 and P2. So I put CP1 dagger, CP2 dagger. So by the way, this is a sum over alpha beta. This is a sum over P1, P2. All right. So this is the second quantization form of the momentum operator. So, and I can also solve this. So sum over all these quantum states P1 and P2. Now my basis states are the momentum states. So these are the quantum states, the alpha 1 and the alpha 2. P1 is an eigenstate of P. So I can write this as, and the corresponding eigenvalue is simply the value of the momentum P1. So this becomes P1 bra P2 ket CP1 dagger CP2. Now this is the Kronecker delta P1 P2 CP1 dagger CP2 P1 sum over P1 P2. Finally, this becomes, I can just get rid of these subscripts P1 and P2. I can just write sum over all P's CP dagger CP. So this is the momentum eigenvalue. And this is a number operator, which tells you how many particles exist with momentum P. So this looks actually really, really fun so far. Now, I can have the momentum operator. I can also have any function of the momentum operator. And its second quantization form will simply be f of p, but these are eigenvalues of the function operator p, cp dagger cp. This is just by extension.
सर
Now, yes, please.
जी इसी तरह से हम हैमिल्टोनियन को भी कर सकते हैं.
बिल्कुल, बिल्कुल. So if our Hamiltonian is p square over 2m, this will simply be p square over 2m, which I can write as h bar square k square 2m. And instead of p, I can write k's over all k's, right? So this is the kinetic energy term for all the electrons. Okay, so this looks good. So what we've done in this, guys, we've kind of started looking at the Hamiltonian for electrons. All right. Now, what about, let me give you another example of another single particle Hamiltonian. Suppose I have a function Vx or Vr. Now, this is an operator written in the position basis. Now, I want to express this in its second quantization form. So how do I do that? My states alpha beta here can be in the real space, they can be in the momentum space. It doesn't really matter. So if I were to look at problems of this kind in which the operator is in the position representation, there are certain kind of definitions that will come to my rescue. So I need to toggle between the real space and the momentum space. So I already know that if I have, I can move from the K space if I were to have an annihilation operator Ck, and multiply this with EIKR, and I sum over all Ks and divide by the square root of the number of particles, I will get an operator in the real space. Okay, so, and I can also write the adjoint of this. Okay, so I can move from the momentum space to the real space. Likewise, I can also define in what in quantum field theory are called field operators. Now, field operators are simply given in the following fashion. So CK, so this is the definition, CKE plus IK dot R. And then I take the sum over K, and I divide by the square root of the volume. Okay. So this is also called a field operator, psi R. So this field operator is a continuous variable operator, and it's just the analog of this. So this is how we define field operators. So what the field operator does is that this annihilates a particle that is located at the position vector R. Likewise, this field operator creates a particle at the location R. All right. So what I've done, I'm moving from the momentum space to the position space. It's exactly so the equations that I've written on the left, they are just continuous variable versions of the definition of the Fourier transform that I have on the right. It's also possible to generally define a Fourier transform. So if I have for any function, so if I have a function R and I multiply this with this exponential factor and I integrate over volume and I divide by volume, not the square root of volume, but the overall volume, then I get the Fourier, I can get the Fourier coefficients at the K points. Okay. And I can also go the other way around. So my FR is this is FR is, since the Fourier space is digital or discrete, instead of the integral, I have this summation of all the FKs, E plus I, K dot R. And I do not have a 1 over under root V or a 1 over V here. So these are definitions that I will use. Okay, so three kind of definitions. One, we've already used these definitions. This is the definition for the field operator. And these are definitions for the Fourier transforms of functions. So some authors would prefer to write instead of this V, 1 over V, they prefer to put a 1 over under root V here and a 1 over under root V here. So these are just author conventions. So don't be bogged down by them. So now I come back to my question of expressing this single particle operator, which is now expressed in terms of a position variable in the second quantization form. So I can actually do that in the following fashion. So my VR in the second quantization form can be written in the following fashion. VR is an overlap between alpha and beta. Now my alpha and beta are the field operators. Psi alpha R dagger, psi beta R. And then I integrate over all of space and I sum over alpha beta. All right. So the creation and the annihilation operators are already embedded inside the field operators, as you can see over here. Right. So ठीक है ना ये बात समझ, so this is just like an expectation value but with different states on the left and the right. Now, what I could do, I could actually express this. I can take these values of the field operators from here and from here and put them in here, here and here. And if I were to do that, so instead of alpha beta, I would like to use the variables k1 and k2. I have d cube r. I get a 1 over under root b from here and a 1 over under root b from here. I get a 1 over volume followed by e minus I k1 dot r v r e plus I k2 dot r ck1 dagger ck2. Okay, so this is just inserting the definition of the field operators into the second quantization form. I can now write this as sum of k2 1 over v. This is the volume operator. So when I write v in the strange symbol, like a bird flying, this really means volume, physical volume, t cube r v r e minus I k1 minus k2 dotted with r ck1 ck2. Now, if I look at these terms, this term,
Dirac delta.
yeah, I get a Dirac delta function. So this term, together with 1 over b, together with this d cube r, I get the Dirac delta function. So overall, what's going to happen is that my overall result will be so what I could do is I could, okay, let's look at the definition of Fourier transform over here. Let's look what we have over here. Okay, if you compare this thing that I've written in the red box, a function of r exponent minus I k dot r summed over all of volume divided by volume will give me the Fourier coefficient at this point k. Okay, so all of this summed over, integrated over all of volume divided by v, all of this thing, what is this going to give me? This is going to give me the Fourier coefficient at this location of this potential of this term. So this is a function in space. This will have a Fourier transform. Let's represent this by this small v, okay, at k1 minus k2. So this is a Fourier term, right? It's a scalar. It's a Fourier coefficient evaluated at k1 minus k2. So all that I've written in red can be replaced by this Fourier coefficient. Sum over k1, k2, ck1, dagger ck2. So this is what the second quantization form of an operator written in the position space looks like. Okay?
Yes, sir.
I hope you do understand the notation. This is a Fourier coefficient
ठीक
evaluated at k1 minus k2. So
ठीक है
what
सर.
we've seen, we've seen example number 1, we've seen single particle operators. Then we've seen a single particle operator which is expressed in terms of position variable, and we use field operators to write it down in terms of the Fourier coefficients. Now, in the example 3 is for the Coulombic interaction. So I would like to do exactly the same second quantization upgrade for the Coulomb interaction. That is no longer a single particle interaction, it's a two particle interaction. And I have many such two particle interactions for my electronic system. So first of all, if I, so my operator, my Coulombic operator, if I look at the term in my Coulombic operator, so this depends upon R1, R2, right? Two variables. So it's a two particle operator. It actually depends upon the difference between R1 and R2. And its form is given by E square over 4 pi epsilon naught, 1 over the distance between two electrons. One is at position vector R1, the other is at position vector R2. So what I would like to do, I would like to write the second quantization form of this, right? And then we'll be able to write down the total Hamiltonian for the system in second quantization form. All right, so far so good. So let's start with the very general thing. So if I have an operator R1 and R2, and I want to write this in second operator form, once again, I sandwich this between the field operators. Psi R1 sum K. So I write K prime, okay, dagger. Then psi field operator at position vector R2 at some other K point, K prime. Okay, and then on the other side, I have psi R2, some other momentum K double prime. Then I have psi at R1, K triple prime. Okay, and then I need to integrate all of this with respect to R1, respect to R2. This is the second quantization form for the Coulombic operator, the Coulombic interaction between two particles. Okay, ठीक है हमजा?
Yes, sir.
Now, one thing that you need to notice is the ordering here. So I go from R1 to R2 to R2 to R1, and sandwiched in between is this operator. So just keep in mind that these R2s need to remain together. This is called normal ordering. Now I can evaluate all of this. So in order to evaluate all of this, I just need to insert the definitions of the field operators. So I just kind of reduce the size, the thickness of my pointer a little bit. And simply I take the field operators that I've defined over here, the green dotted expressions, and I put them back into this expression. So there are four 1 over under root b. So I get, first of all, I get 1 over b square. Right? So, and then I need to sum up over all the k's. K, K prime, K double prime, K triple prime. So I need to sum up over all the k's. This V R1, R2, I just write as it is. And then I need to write exponents. So the field operators in the dagger form give me E minus I K R1, E minus I K prime R2, E plus I K double prime R2, E plus I K triple prime R1, followed by the the creation and annihilation operators. So C K dagger CK prime dagger, CK double prime, CK triple prime. Okay. So this is all looking good. So now the next step, I simply look at the first term here, this exponent and this exponent. Okay, and then I kind of combine them, E minus I, K minus K triple prime, R1. So all of this is now acrobatics, mathematical acrobatics, E minus I, K prime minus K double prime, R2. VR1, R2, sum over all Ks, 1 over volume square, and d cube R1, d cube R2. All right, so from this point onwards, it's actually quite simple. So what I could do now at this stage is the following: d cube R1, d cube R2, 1 over volume square, all Ks, V, write this as R1 minus R2. And then I write this term here as E minus I, K minus K triple prime, R1 minus R2. So on purpose, I have added this term minus R2. So I also need to kind of counteract this minus I, K prime, K minus K triple prime plus R2. But I also have this term here. So E minus I, K prime minus K double prime R2 with all of this, okay, with all the creation and annihilation of CK dagger, CK prime dagger, CK double prime, CK triple prime. Now in the next step, I could, Hamza, I could replace this R1 minus R2 by a new vector Z. Replace this by Z. So I want to get rid of the R1s. So now I have a sum over dz in 3 dimensions and dr2. 1 over volume square, all k's, v r1 minus r, v, sorry, this becomes v of z, e minus I, k prime, k, sorry, k minus k triple prime dot with z, e minus I, k minus k triple prime plus k prime minus k double prime with R2, ck dagger, ck prime, ck double prime. All right, now we can actually do something really, really interesting. If you observe carefully, this term and this term only has a z in it. And I can combine this with this integral, d cube z, and take out one of the v's. So I'm really kind of looking at the Fourier transform at this location of this potential, correct? So I'm just invoking this definition of the Fourier transform again. So now I have a function of z here. Here I have a function of z. This is a function of z, and I'm integrating over z, and I'm just employing one of these volumes over here. So when I do that, I get d cube r2. I'm left with 1 over v all k's, and I take the Fourier transform of this potential of the electrostatic potential V at k minus k triple prime, right? So all of this becomes this. I'm left with E minus I k minus k triple prime plus k prime minus k double prime R2 ck dagger ck prime dagger ck double prime ck triple prime. Now, as you can imagine, things get really, really easy here because only this is the term that has an R2 in it, and I need to integrate over R2. So what I do next is I kind of change the order of things a little bit. I have all k's, V, the Fourier transform at k minus k triple prime, and then I take an integral d cube R2. I prefix this with a volume, E minus I, this giant string of k's, R2, followed by my creation and annihilation operators. Now, once again, this is a Dirac delta function, where this term is to be 0, correct? So all of this then becomes all k's, Vk minus k triple prime, a Dirac delta function. Now I express that Dirac delta function as, so the Dirac delta function imposes, the Kronecker delta function imposes that this combination has to be 0. So I express this as k triple prime is equal to k plus k prime minus k double prime, followed by ck prime ck triple prime. Now this means that k prime is equal to this thing. So this term becomes bk minus k triple prime. This becomes k double prime minus k prime. C k prime ck double prime triple prime becomes k plus k prime minus k double prime over all k's. Now there are only 3 k's that remain. Remember, k triple prime has been taken care of. So this is the second quantization form for the Coulombic interaction. Beautiful. Really, really, really beautiful. So what I could do now is express this in an even prettier fashion. If I suppose define this variable to be P1, if I define this variable to be P2, I define this variable to be the momentum Q. This is just a relabeling. Then you can show that this term here, K prime, is given by P2 minus Q. And this term will be given by P1 plus Q. Okay. So just relabel the momentum operators. So this is something you can check on your own. So let me give you one example, one check. So K prime is So we know that K prime is excuse me, K prime, K double prime minus K prime is Q. So K prime is K double prime minus Q. But what is K double prime? K double prime is this thing, P2. P2 minus Q. So in this way, this is a consistent definition or a relabeling of all these combinations of momenta. Overall, what I have is the second quantization form of VR1 minus R2 becomes, remember, V is any function which only depends upon the difference between two variables, R1 and R2. So this becomes sum over P1, P2, Q, the Fourier transform of this function V, of this function. So this is the Fourier transform of the function. The Fourier transform is expressed in the K space or the momentum space, and this is evaluated at Q, followed by CP1, CP2, CP2 minus Q dagger, CP1 plus Q dagger. And this is a key result, key result. Now I can express this in I can express this in terms of a Feynman diagram as well. So what this interaction, this Coulombic interaction is really representing, I am creating, annihilating a particle P1 of momentum P1, annihilating a particle of momentum P2. Then there is this interaction VQ, and after the interaction, I'm creating a particle of momentum P2 minus Q and a particle of momentum P1 minus Q. So if I draw a Feynman diagram for this, I have a particle of momentum P1 coming in, a particle of momentum P2 coming in. Then there is an interaction between the two particles, which is the Coulombic repulsion. In this interaction, a particle of momentum Q is transferred from P2 minus P1. And after the interaction, the first electron moves away with a reduced momentum P2 minus Q, which is given here. And the second particle moves away with an enhanced momentum P1 plus Q. So there is an exchange of a quasi-particle between the two electrons, which accounts for the interaction. So this is the general scheme of how we create two particle interactions and express them in the second quantization form. So, ठीक है हमजा?
Yes, sir. ठीक.
All right. So I think there are more participants as well. Sorry, I did not recognize that. Anyway, एक मिनट में शेयरिंग रुकी, एक मिनट. Can you see my OneNote screen?
Yes, sir.
But I can't see it. All right. So now what we need to do next really is we need to find out the Fourier transform for a Coulombic interaction, for our Coulombic repulsion. Our Coulombic repulsion VR1 minus VR2 is of course given by E square 4 pi epsilon naught R1 minus R2. So this is between two electrons. So we really need to sum this up over all the electrons of the system. So how do we do that? So one way of doing that is, we want to see what's the Fourier transform of this function, correct? इसका मालूम करना Fourier transform. And then we evaluate that Fourier transform at our desired value of the momentum. So we want to compute this, given a 1 over R relationship that we have for the Coulombic repulsion. So how do we find out the Fourier transform? In order to find out the Fourier transform, let me derive that. But first of all, let's start with an expression that I write 1 over q square. Q is some momentum EI q dot R, and I sum over all q's. Let's see what this expression is. Okay. In order to see what this expression is, first of all, if there are lots and lots of momenta, if the k space values are finely spaced, I can replace this sum over q's by an integral. And we all know what that is. So I can replace this by v over 2 pi cube sum over d cube 1 over q square EI q dot R. So this is our conventional replacement of this discrete sum by this integral. We know that 2 pi cube over v is the spacing between two cube points in a three-dimensional space. So this discrete sum can be written as an integral. Now this integral can be solved pretty easily. So if you're in the three-dimensional space and the three-dimensional volume element becomes v over 2 pi cube, this becomes a three-dimensional integral. One is with respect to phi, one is with respect to theta, one is with respect to q, and we also have q squared sine theta, which is the metric. Phi goes from 0 to 2 pi, theta goes from 0 to pi, and q goes from 0 to infinity, and we have E I Q R cosine theta. Okay? So this is the value of this discrete sum. If I were to do all of these calculations, it's pretty simple to do. My final result. So let me kind of advance a little bit forward and see what this looks like. This is 2 pi over here, and I'm left with d theta, dq, there's a q square as well, right? This q square just cancels out. dq sine theta, EIQR cosine theta. So in the next step, I kind of do a substitution. I take cosine theta to be equal to z. This sine theta together with the d theta gives me dz. The limits will also change. So this will become an integral over z. And lo and behold, finally, my final integral will look like this. Okay, 1 over r. So this is sum over all q's, 1 over q square, EIQ dot r. So what this also means is that 1 over r is 4 pi over the volume q 1 over q square, 1 over q square EIQ dot r. But we already know in a sense that, by the way, let's put 1 over, let's put E square over 4 pi epsilon naught 1 over r as well. So this gives me the full potential. This becomes E square over epsilon naught volume Q 1 over Q square EIQ dotted with R. So let's compare. So this is a function of R, some function of R, and it readily shows that this term over here, this term over here, this term is simply the Fourier coefficient. How do I know that? So if I go above to my definition of the Fourier transforms, which are here, notice the correspondence and the likely resemblance of what I've written at the bottom with this function, right? So it's just a sum of the Fourier coefficients being multiplied by plane waves. So this is exactly what we have over here. So the Fourier transform of the Coulombic repulsion at the value Q is given by E square epsilon naught V and Q and a Q square. Okay. So if instead of 1 over R, we had 1 over R1 minus R2, that will simply replace this R with R1 minus R2. And then I can replace this with a Z as I've done before, and exactly the same result will be obtained. So the Fourier transform of the Coulombic repulsion, this is the Fourier transform of the Coulombic repulsion. Okay, so now I can write down the overall Hamiltonian. The overall Hamiltonian in the real space is given by P sum L square over 2m, sum over all the L's, where L's are all the particles, plus VR1 R2. So, right, and then you sum up over all the R1s and all the R2. So if I were to write this, I would simply write this as the sum of all R1s and R2s. So in the second quantization form, and by the way, so this is really E square over 4 pi epsilon naught. Let's write this in this fashion: 1 over Ri minus Rj, sum over all i's and all j's where I is not equal to j, correct? And we also need a factor of 1/2 in order to avoid double counting. Okay, so this is my Hamiltonian. We've seen this Hamiltonian in one of the early lectures as well. So now in the second quantization form, this Hamiltonian is going to be represented as sum over all the momentas h bar square k square over 2m plus 1/2 of this Fourier coefficient, this thing, E square over epsilon naught volume Q square, and then CP1, CP2, CP2 minus Q dagger, CP1 plus Q dagger, summed over P1, P2, and Q. right? So this is our Hamiltonian for a sea of interacting electrons. Any questions? We
नहीं
still
sir.
have 10 minutes to go. ठीक है? All right. So can I move on?
Yes sir.
अच्छा ठीक है. एक मिनट बस. Right. So all right. So let's move on. Now, do you notice anything bizarre in this formula? Anything strange? Any term that diverges?
सर ये होगा कि when Q की जो when Q approaches 0 तो फिर तब diverge करेगा.
Right. So how do we rectify this divergence? So is something missing in this Hamiltonian? So if Q is equal to 0, then the repulsion just diverges. So how do we correct it? So in order to correct that, एक मैं स्क्रीन को जरा हैंडल कर रहा हूँ एक मिनट. एक मिनट ये स्क्रीन को मैं किसी तरीके से एक मिनट स्टॉप शेयर करता हूँ. All right. So in order to counteract this divergence or mitigate this divergence, there's another term that needs to be considered, and that is the influence of the positive ions in the system. Now, you also have these electrons are not in vacuum, they're inside a solid, and inside the solid, there are positive ions as well. And so in the jellium model, we assume that these positive ions form a homogeneous number density, a homogeneous distribution of ions, and those ions produce an electric potential. So the potential at some position vector r is, of course, it's from your basic electrodynamics, you would know that this is given by E times the number density so the ions exist at position vectors r1. So the ions are at r1, and you want to find the electric potential at r, right? So this is the problem that we have in front of us. So the number density is at r1. You multiply this with the charge on an ion. Suppose that is E. You're assuming monovalent atoms. And then you have 4 pi epsilon naught r minus r1. And then you kind of integrate over all the locations of the ions, d cube r1. This is my electric potential, correct? Now, if I know the electric potential and I have also the electrons, then the number density of electrons, if they are homogeneous, as they are in a free system, the number density of electrons will be the same as the number density of the protons. So the Hamiltonian, due to the electron ion interactions, will simply be given by the number density of electrons. The electrons are now at R because we're looking at the interaction between electrons and ions. The electrons are now at R. So the electrons are here and the ions are here. So you multiply the electric potential produced at the location of the electrons from the ions with the number density of electrons, and then have nr1 and then you divide by 4 pi epsilon naught r minus r1. Now you need to integrate over both the location of the ions and the electrons, and then you need to divide by 1/2 as well in order to avoid double counting, because if electrons and ions switch positions, it causes the same amount of energy. So all of this now becomes minus, by the way, there's another e here, minus e square 8 pi epsilon naught. We can separate out the impact of after not right now, d cube r and r over r minus r1, or you can use r prime as well. So now what does this mean? I can write this as minus e square 8 pi epsilon naught. This is number of electrons per unit volume or number of ions per unit volume squared, d cube r1 d cube r1 over r minus r1. Now we can use our relationship that we've derived over here. 1 over r can be written in this form. So we just put that back into the expression. So this becomes minus e square 8 pi epsilon naught n over v whole square. And we pick up this factor, this 4 pi over v. 4 pi over v sum over q d cube r1 d cube r2, sorry, d cube r1 and r. If you don't mind, I'm going to use r and r prime, if you don't mind. So this is 1 over r minus r prime. So let's stick to r1, and we've already used r1, so let's stick to that. G cube r1, r minus r1. Sorry, this is to be replaced by 1 over q square e minus iq dot with r minus r1. Okay. Okay. So this becomes minus e square over 8 pi epsilon naught n over v square 4 pi over v sum over q 1 over q square t cube r1 e minus I e plus iq r1 d cube r e minus iq dot r. Okay, so if you notice that if I look at this term, this is v into the Kronecker delta q dot 0. This is another v Kronecker delta q dot 0. So there's a v here and a v here and a v square here, and some cancellation occurs, minus e square n square 8 pi epsilon naught 4 pi over v. Can actually get rid of this 4 pi here. This is with a 2 minus e square is v 1 over q square delta q 0 squared of a Kronecker delta function is a Kronecker delta function. Okay.
सर
जी
सर जो आपने थर्ड लास्ट लाइन में जो एक्सपोनेंशियल लिखा है उसमें ये पॉजिटिव आर्गुमेंट नहीं होनी चाहिए या फिर नेगेटिव ही है?
फर्क तो नहीं पड़ता, पॉजिटिव लगता है, फर्क पॉजिटिव होनी चाहिए लेकिन फर्क नहीं पड़ता. ओके
ऑलराइट
ठीक है, शुक्रिया. So this is an additional term which arises due to the interaction between ions and electrons. So overall, I have H becomes H bar square K square over 2m summed over all Ks plus half E square epsilon naught V Q square sum over P1, P2 and Q. And then I have CP1, CP2, CP2 minus Q, CP1 plus Q. By the way, these electrons can also have spins. So these are spin particles. So let me introduce the spins here. And first of all, let me write this extra term minus E square N square 2 epsilon naught V sum over Q 1 over Q square delta Q0. So this is also a divergent term at Q equals 0. This is at Q equals 0. So this is just has one value of Q, that is Q equals 0, but it's with a minus sign. So that's going to help us. By the way, if I were to introduce spin into this system, we're talking about magnetism, so spin must be there. The P1 particle can have spin sigma 1, P2 particle can have some spin sigma 2, P2 walks away with the same spin as original sigma 2, and this has a spin sigma 1. So this is, and then I need to sum up over all the two kind of sigmas as well. Okay. The sigmas could be positive or negative or up and down. So this really means that if I look at my Feynman diagram here, then my this is sigma 2, this is sigma 1, sigma 2, sigma 2 here, and sigma 1 here. Okay. So I can, so my quantum states now exist of both momentum and spin variables. So this is my overall Hamiltonian. Now, if you look at this term, and if you insert Q equals 0 here, if you insert this term, let me insert Q, let me look at this term when Q equals 0. So when this term is Q equal to 0, I have 1/2 P1, P2, E square epsilon naught V Q square All right, so I'm really sorry. My internet just kind of broke down for some unknown reason. So I just restarted. I'm just going to finish this so that I can complete the lecture, just 2-3 more minutes. I'm sorry for this interruption. Lost some people here, but that's all right. We're going to record this anyway. So let me share my screen, just ending up my, okay, so I share. Right, so एक मिनट मैं इसको जरा ठीक कर लूं सूरत हाल इसको मैं जूम कर लूं इसको So overall, what I have is, okay, CP2 dagger, CP1 dagger. So this is this term over here. So if I notice, this term becomes half P1, एक minute. So half E square over epsilon naught V Q square delta Q0 sum over P1. Now these two terms can be combined, and the P2 terms can be combined. And why can I kind of change the position of these terms? The reason is that when I swap two fermionic operators, I incur a negative sign. So when I move CP1 to this location, I incur a negative sign. And when I move it 1 point forward, I get another negative sign. So overall, two negative signs make positive. So I have CP1 dagger CP1, which is just a sum over P1s, and I have a sum over P2s, CP2, P2. But this is nothing but the number of particles. This is also the number of particles. So I get E square over 2 epsilon naught V Q square delta Q0 N square. And this is exactly equal to the term that we have over here. But this is with a negative sign. So at Q equals 0, that term is automatically cancelled out by the electron ion interaction. So the divergences are taken care of adequately. So overall, the Q equals 0 terms do not exist. So the final Hamiltonian is h bar square k square over 2m sum over all k's plus 1/2 E square epsilon naught volume Q square sum over momentas. I'll just write down the momentas in a minute. CP2, CP1, CP2, CP1 with some sigma. हमने क्या कहा था? Sigma 1 कहा था इसको. This is CP1, CP2, sigma 1, sigma 2, CP2 minus Q, sigma 2, dagger, CP1 plus Q, sigma 1, dagger. You need to take the sum over P1, sum over P2, and you need to take a sum over Q, but Q cannot be equal to 0. So this is the Hamiltonian for interacting electrons, which are connected together by the Coulombic repulsion. So what we've done today, oh, I think I did not record the last bit. I don't know. Oh no, I think it's being recorded.
आई थिंक
So
ये ऑटोमेटिकली शायद मेरे पे रिकॉर्ड हो रहा है,
वो
बिकॉज
हो
जब
रहा है,
आप जी
ठीक है, बिल्कुल हो रहा है।
ठीक
तो ये थी हमारी कहानी आज की। In this story, what we've done, we've started with the idea of the number, occupation number representation. Then we've upgraded operators to the second quantization form. The second quantization form treats everything as a particle, waves as particles, interactions between electrons and particles as particles. So interactions become particles as well. This is a particle with the momentum q here. And then we were able to write down the Hamiltonian for this system. Now this Hamiltonian can be diagonalized. It's not diagonal at the moment. It can be diagonalized, and one can find the energy for this sea of electrons which are inside a homogeneous soup of positive ions. Now, when we find out the energy values for this electronic system, we can then move on to combining this idea with the idea of the tight binding Hamiltonian and see whether systems under what conditions they become ferromagnetic or they remain paramagnetic. So this was the overall kind of import of today's lecture. And I'll be uploading this soon. So thank you, Hamza, for your time.
मोस्ट
Inshallah.
वेलकम सर। ठीक है सर, एक बात छोटी सी पूछनी थी। मैं घर आ गया हूँ गुजरात, तो अब जो थर्सडे का लेक्चर है, मैं वैसे एक दफ़ा स्टूडेंट से और भी कुछ बात कर लेता हूँ कि अगर उनके लिए भी ऑन कैंपस मसला हो तो फिर हम या तो ख़त्म कर दें, पॉसिबिलिटी
देख
अगर
लेते हैं,
उसकी
वो
है।
ना भी डीन की भी ईमेल आई है कि एमएस स्टूडेंट्स वगैरह भी ऑनलाइन ही होगा, तो मेरे ख्याल में ऑनलाइन ही करेंगे।
ठीक, चलें,
ठीक है, चलें जी, चलें
थैंक
जनाब, ओके जी, अस्सलाम
थैंक
वालेकुम,
यू,
खुदा हाफिज़,
अस्सलाम वालेकुम।
अस्सलाम।